An 80 kilogram man standing in an elevator on a bathroom scale. The bathroom scale is calibrated to kilograms. So we want to know what will happen. So, I mean, I guess the thing you need to know is if this guy is standing in a bathroom scale that's at rest, the forces would be force of gravity, normal force. A would be 0, and we would have that MA is the sum of the forces. A equals Fn minus Fg. So we would have that Fn equals mg, which would be 80 times 9.8, which equals, my calculator, 80 times 9.8 is 784. So if he was in his bathroom or anywhere other than in an accelerating place, hit the scale. Okay, so why did I calculate Fn? Because like we've said, anytime it says scale reading, how heavy does he feel? Heavy he feels, or his apparent weight. All these things go back to the normal force. Okay, and then in order to convert it to go from there to kilograms, it's just dividing it by 9.8. Now we look at him and he's not in a zero frame of reference, so all this is kind of irrelevant. So what is happening, they tell us, is that the elevator is accelerating down at 3 meters per second squared. So it is accelerating. So when we go to solve this, we're going to say MA equals the sum of the forces. And then, so now we know the mass is 80. We know the A is 3. And what is the sum of the forces? Well, let's draw our free body diagram. I guess we jumped the gun here. We do have an Fn there, and we have an Fg there. The fact that he's accelerating down means that Fg is going to be greater than Fn. It's often convenient to make the direction you're accelerating positive. See, we kind of did that automatically because we set 3 equal to positive and not negative. If I wanted to make up positive, I would have to set this to negative. That's an extra step that is sometimes tricky to remember. So we have Fg minus Fn. And since it's asking us what will the scale reading be, we're looking for Fn. So I'm going to solve for Fn, which equals 80 times 3, and then, sorry, that's not right. It's going to be, let me erase that. It's going to be, let's just rearrange this. Fn is going to equal Fg minus, and I'll just call it MA for now. Plug the numbers back in. So really what we're doing here is Mg minus MA, which equals 80 times 9.8 minus 80 times 3. And when you solve all that, you get, let's see, 80 times 9.8 minus 80 times 3, you get 544. That's in newtons. So my normal force in newtons is 544. The scale is calibrated to kilograms. So in order to find the apparent mass, we have to take the normal force and divide it by 9.8. So divide that by 9.8 and we get 55.5. And that equals 55.5 kilograms. So what this is telling us is that this 80 kilogram man, when accelerating downwards at 3 meters per second squared, feels like he's only 55 kilograms. I'm sure that feels pretty good. You're 30 kilograms, almost 25 kilograms lighter than you actually are. So that's one way to lose weight. You're not. So just to be clear, you're not actually losing weight. Your force of gravity is still mg. But because how heavy you feel depends entirely on the normal force, what that means is that the normal force is smaller than the force of gravity force of gravity is 784. The normal force is 544. So the ground is only pushing up on you with a force of 544. That's how heavy you feel in this problem.